So about this section that is devoted to intervention, let's see, and my focus will be on physical intervention, but trying to speak something about a new way to model the physiological adaptations, and it is something related to the network science. And so network science has its basis on, or even better, network physiology has its basis on network science. And network physiology arrived about 10 years ago, after a long journey, starting from systems biology and integrative physiology. And as a matter of fact, systems biology is data-driven, and integrative physiology is concept-driven. It is devoted to understand the mechanism that led to homeostasis, and both of them overcame the reductionist biologist framework, let's say, and so in both cases we are dealing with complexity. I suppose, or I think, I strongly think that every time we are dealing with some adaptation or with some mechanisms into human body, we are dealing with something about variability and complexity. And so we cannot study a single part without integrating it in a plethora of systems and subsystems. And so, okay. And so, as I said, in network physiology, something about 2012, the first references, probably, with a group of Boston. Probably the leader was Plum and Imanov. And most of network physiologists came from mathematics, or even better, physics. So most of them are still physicists. And in fact, they were trying, and they are still trying, to use mathematical and models and physics, let's say physical framework, to model the human physiology. Most of them use time series, and so they try to couple time series or to detect some causal relationship among systems and subsystems in a dynamical interaction. So the framework lies on the fact that health or physiological states emerge from interconnectedness of systems and subsystems. Each system has a proper own regulatory mechanism, but continuously interacts with other systems and subsystems. And so integration, interconnectedness, dynamicity, complexity are all keywords of network physiology. Also, so network physiology, as I said, is based on network science. So network science is used nowadays in a plethora of disciplines, and is based on modeling the graphs. So it's based on mathematical graphs, as we can see here. If I'm able to, okay. As we can see here, there are some examples of networks. And so, for example, we can see as a set of nodes and a set of edges that connect the nodes. And so this is a reference of a real famous scientist on graphs, that is Barabasi. And in my study, we will deal with weighted networks. Weighted deals with the fact that the edges are not binary, so with or without edge, but are linked to a weight. In our case, we are dealing with correlation graphs. So basically, and the weight is the correlation coefficients. Here are other kind of graphs, and are based on matrices, and these matrices can be modeled quite easily. At a glance, they don't seem easy, but I really think that they are theoretically easy. And so, for example, in the weighted networks, we are dealing with a matrix of correlation coefficients, so we can deal with it. And so let's put it, okay. Here is an example of a group of Mexican scientists really devoted to use network model to deal with health and disease. So in last years, they published quite a lot of papers. Actually, two are the main papers. One is this one last year, and they published very recently another one dealing with network models and health. And so I have to introduce some topics about network science. One is density, that is simply the ratio between observed edges and total edges. Global transitivity is that if a node A is connected to node B, and if node B is connected to node C, so the probability of node A to be connected to node C. Okay, so the characteristic is path length instead is the average number of edges in the shortest path between all nodes, and we can think about the 6 steps of small world if you are familiar with this topic on social sciences, though each person is connected by each other by on average 6 steps. So this is the measure, and clustering coefficient is actually the extent to which our graphs tends to be clustered in subgroups. Okay, and so this group of Mexican scientists studied some graphs of metabolic nodes across ages or across age groups. And so, as you can see, they found several differences in several measures across ages. So their idea is that in aging, we usually lose a set of connections, and so our physiological network is more prone to be damaged. So in our group, we are used to study the effect of different type of trainings in elderly. And so we are dealing with training specificity, so the differential effect of any training type. So we study before and after, or even better if we can in the follow-up to, or throughout the protocol. And basically we study endurance, neuromuscular electrical stimulation, and resistance, so active and passive type of trainings. And so we try to understand the physiological mechanism that drive the specificity of any training. And so here you can see some specific effect dealing with cells, with redox system, with hormonal system, and we identified some differential response of training type among strengths that we called bars, bottom-up rise strength transfer. That is basically training the lower limbs. You can have effects of upper limbs, and it cannot be related to neural mechanisms that drive, for example, the cross education. And so we started to think about some systemic factor that drive this systemic adaptation. And as you can imagine, systemic adaptation is perfect to be linked to network models. And so we identified some differential response also on functional mobility, 5 times into 10 times, and timed up and go test. And so starting from this framework of training specificity, we had a set of data before and after the training types, and we tried to understand it on a different perspective related to network science. So applying network models for building the graphs, analyzing the global and local measures, and try to compare the graphs. Each graph is related to a set of motor or physical or physiological parameters in elderly, and at the end discussing how the complex model we identified in human physiology. So the framework is based on this project that is ongoing since, if I remember well, more than 10 years ago, that is called AMA, the Italian acronym mean Attività Motoria Adattata, and LOWS, the third age. And so it's based on a multi-parametric evaluation, as we can imagine, some cellular measure, some molecular measure at the beginning, but still now a big focus on muscle physiology and stem cell, muscle cell stem cell physiology, but also some posturometric measure and some motor outcomes. So the methods here is about 70, not about, it's probably 71 participants and 12 years of analysis. And the whole set is bigger, but to this extent, I identified this subset because it's adequate to run the analysis. So 24 subjects trained with endurance protocol and 47 trained with neuromuscular electrical stimulation. The duration was 8 to 12 weeks, about 3 times per week. And the endurance was based on stationary bike with heart rate training. Even better, the training was based on heart rate, identified with some formulas about the adequate window. 30 minutes, and then in last weeks, 40 minutes, and with increasing intensity. Neuromuscular electrostimulation was based on a protocol, customized, based on some references, 18 minutes, with relatively high frequency, so 75 hertz, and about 6 seconds of stimulation, 4 seconds of active stimulation, let's say with rectangular steady state. And talking about the network models, at the beginning, we checked for multivariate normality. So we applied a non-paranormal transformation, and we ran partial correlation. That is the normal correlation correcting for other measures. For example, if we have 4 measures, I can run the correlation between 2 measures, correcting for the other 2 measures. So we deal with all the measures. It's a kind of multivariate framework. And so some other technique, regularization, and one other based on Bayesian statistic to build the model, and then try to run some new statistical tools to identify the confidence interval for the edges, and for to run significant differences about the centrality measure. Centrality measures in network science are those measures that can inform us about the main nodes into the networks. In each network, except for lattice model, that is, we have main nodes and peripheral nodes. So we can measure some marker of centrality. And so to compare the networks, so we had 4 networks, 2 about endurance before and after the training period, and 2 about NMS before and after the training period. So we started to think, okay, but now we have to compare these networks, no? Because we want to see the differences about training specificity. And so we ran some other analysis. One is a common measure in network science, the Jacquard Similarity Index, but we dealt with weighted network about correlation coefficients. And so we ran also the weighted Jacquard Similarity Index. And I played a little bit trying to deal with negative coefficient. And so we applied 2 other modifications, let's say, of this measure, not just because I wanted to play a little bit, and I suppose it was useful. And so, as we can see, the density that we should remember is the number of edges on the total number, the number of observed edges. So high correlation coefficients on the number of total edges.
5 minutes left.
Okay. So there were several differences, and each measure revealed a different adaptation. So these are the statistical tools I was talking about. This is the stability of edges, but I don't want to enter in details about this, but just to have robustness of our analysis. And these are graphically the 4 graphs. Okay, as we can see, we clustered arbitrarily at the beginning in anthropometric strength and functional mobility measures. And so, as a matter of fact, we identified that endurance group underwent a more marked alteration of the interconnectedness of parameters. And so about the conclusion, we think that a cross-sectional evaluation at baseline with network models can inform us about some subtle differences that can bias our adaptations. And so the effectiveness also of training types can be identified about network models and with physiological adaptations. And we have to implement a set of measures because each measure can reveal us a different type of adaptations. And so other groups are dealing with this. Basically, these are a group of Canadian mathematicians that are trying to identify the network model of physiological biomarkers in elderly to predict the health trajectories. They are really interesting course, and they are working so hardly in this topic. These are all recent publications of that groups. And we are still trying to identify the physiological mechanism or physiological factor that drive the systemic adaptation that are basically called nowadays exerkines, so cytokines secreted by exercise or in response to exercise, and exersomes that are the extracellular vesicles secreted in response to exercise that we strongly think that drive systemic adaptations. And there are several possibilities, luckily, nowadays, to have, because obviously the problem is that having a big set of parameters to run a really robust analysis. But nowadays there are several possibilities. This is a really large database. It is a consortium, really recent. They are publishing now their results, first about mice, but in next months I hope they can publish their big data set about human adaptation to different exercise protocol in elderly. So big database will be available to anyone, and even about these are basically before and after biomarkers, but we can have also larger database about time series analysis. For example, if you want to measure heart rate during the training, or some neural measure to link with muscle measures. So this is another large database currently available in since several decades ago, but nowadays implemented. And so we just to show that there are several possibilities to have a set to have a large set of data to run our advanced analysis. And this is
Danilo, I'm
yes,
very
I finished.
sorry. Danilo,
I finished.
I am very sorry to be impolite, but we are very late.
Finish it. Look, probably this is the reference. This is just the last figure to model. I mean, this is a theoretical model of several systems that drive systemic adaptation with two current principles of metainflammation and oxyinflammation that we are studying. So we have several ongoing studies about this kind of framework that is, I mean, theoretically, but